First, we have Rajie Kamani, CEO of Auradine. And I got a question for you about secure compute. It's important in the blockchain. How soon are we going to see it being equally important in what we're talking about with AI?
So maybe I'll start with a little bit of context on what I'm involved in, just briefly, and before I answer your question.
Why I teed you up.
Yeah.
We'll get that out of the way, and then we're going to go.
Yeah, so AI is an incredible disruption that we all love because it gives us tremendous opportunities to create new products and solve tough problems. Me personally, I've, in the last 3 years, founded 3 companies. One is Auradine, which provides low-power technology for blockchain as well as for AI, and I'll talk in a second about that. The second one is a company called Upscale AI, which builds the network, open network for AI compute and rack-level solutions. And then the third one is AI cybersecurity, securing the use of AI. Okay? And today, in the chips and compute, it's really the first 2 companies. So going into, just very briefly, what we do at Auradine is that we started out applying low-power technology to blockchain and in particular Bitcoin chips because Bitcoin consumes power. The density of power in Bitcoin leads AI data centers by about a couple of years. So we have, and we are shipping like 3-nanometer chips in volume production as part of systems. We do cooling technologies. Both we are shipping and actually deployed immersion cooling technologies, which a lot of people believe is not possible, but we are shipping that in volume. We are also doing liquid cooling technologies at rack scale solutions. And then in the AI networking, we are building racks where anybody who's doing an AI compute can come and plug in, and we provide the scale-up, scale-out infrastructure.
So then the question was how lessons from blockchain can be applied to AI.
Yes, so the way we are doing it is that in the blockchain, to achieve low power, we take advantage of the V-squared effect, right? So as you know, power is a function of voltage squared, and among a few other things, capacitance and switching and so forth. But we run these chips at near threshold voltage. So your typical AI chips run at like 0.75 volts. We actually run it like below 0.3 volts, so we get a V-squared benefit. Now, to say that is very easy, to do that is very hard because you have yield issues, your reliability issues, your frequency drops quite dramatically. And so the only way to do it is through custom circuit design. We build our own libraries, arithmetic libraries for it. We work very closely with foundries, and we are applying that to AI. Okay, and so we are engaged with a few large cloud customers and people who are building these leading-edge AI chips. Some of the names you know that are super interested in using that for AI.
Faraj, you're next on our lineup here. Tell us about Cognit Chip, and also specifically I'd love you to address the interconnect problem, which I think you guys obviously with your working on semiconductor solutions would be right in the middle of that kind of a chip-to-chip, chip-to-memory type stuff. So that seems a big gating issue. And what do you guys work? Tell us what you do and how you're solving that.
Sure. So if you look at all the applications today in AI that we're all talking about, they go from standing still to getting 10 million or 100 million users on their network, on their application. The problem is the chips that were designed that they run this on were conceived probably 7-8 years ago, and we're starting design on about 6 years ago. So there's no way they could have comprehended this kind of scaling this fast. The fundamental problem in our industry, and the hidden problem that a lot of people in the semi industry don't know, they hear about it, but they don't know how deep it is that the chips take too damn long to design, and they're too damn expensive to design. We used to have 200 startups getting funded in Silicon Valley to do chips. For the last probably 15 years, it's averaged in single digits. And the fundamental reason is what I just described. So having built 2 semiconductor companies and taken them public, I know the problem really well. So what we set out to do here is to collapse that time and democratize it. So how do we do this? We are developing a physics-informed foundation model ourselves and cross that with essentially software development capabilities, kind of like what people talk about in the software industry is, vibe coding. You can't vibe code chips. So what we need to do is to create something very similar, but for chip designers. So it's, if you will, it's an intersection of something like an Anthropic would build, but only for the vertical of semiconductors, cross it with something like Cursor would build, but for chip designers. And that's, we're hoping to be able to bring value in that way, where we collapse the time to do it chips. And we think we can reduce the cost of developing a chip, the development cost, not the production cost, but the development cost by about 75%.
Sichu, you're next. For our systems, you're working on cooling, which again, it's another gating factor. Maybe tell us how you're attacking this. These are all gating factors, and you've got a big one there.
Yeah, I'm the founder CEO of Floor Systems. We are entirely focused on cooling solutions. We are a 6-year-old company, so when we started the company, there wasn't any generative AI yet. However, we could see that all of these compute platforms are going to be limited by the cooling capabilities that you're going to have, because you're talking about gigawatts of power being consumed by AI data centers. The reality is that all that power converts to heat. And if you don't have a very efficient means of removing heat, then you're not going to be able to actually run your data centers at that level of performance. So, and this problem is not just in the data centers, it's also at the edge. If you take any consumer device, they have a certain amount of performance, and very often that's dictated by how much heat you can actually remove from the device. I mean, a great example is, Apple Mac devices. You could have a MacBook Air, or you could have a MacBook Pro. And the dirty little secret is they both use exactly the same chip, which is the Apple Silicon M series, M4, let's say, the latest. However, there's a big difference in the performance between those two platforms. In fact, you have to pay like $400 to $500 more for the MacBook Pro compared to MacBook Air. But really, the only difference between the two is the heat removing capability of the two. So
when I buy a MacBook, I'm really just buying an air conditioning system when I buy a MacBook.
You're not buying an air conditioning system. You're actually literally buying a fan and paying $500 for
An
it.
expensive fan.
You're not just paying that extra
Big ass fans. They're now doing deals with.
It's not. It costs $20. But the problem is not just what you're charged for that extra performance. The problem is you're also forced to lug around a device that's very thick and heavy and noisy. Those are the indignities you ought not to put up with. So what we discovered is that there's a great opportunity to bring in new thinking into both cooling edge devices as well as data center devices. And all of us in our company come from silicon background, semiconductor background. So we've actually seen how the semiconductor industry has completely changed the landscape in terms of the speed at which you innovate and also the manufacturing processes and techniques that you have. I mean, we are talking about 2 nanometer technology now for semiconductor. But when you think about thermal, traditionally, it uses mechanical technologies where the manufacturing process is very archaic. It's almost 19th century. So our company is bringing new thinking and creating incredibly new disruptive technologies for improving cooling both at the edge as well as in the data center.
We're going to get into that. All right, last but not least, my friend Dinesh, or as I call him, the Marlboro Man of semiconductors. You're the only guy who, I like to be the handsome guy with the hat, because I'm the only guy with the hat. So, and you always, a style icon in your field. Listen, you've done this at so many different places. I just want a more, and you're working on so many different things. I want a more general question about right now when we're architecting these systems. What's the factor in trying to get it into market versus getting something that's bleeding edge and can really move the needle? How do you balance that and toggle that in all the different things you're working on? And maybe you can even give examples from things you're working on.
Let me start with the dimensions that will give us an order of magnitude improvement on the compute side. And we need improvement on the compute side because for AI, compute needs to be as cheap as water. Without it, it doesn't serve the societies across the world. Not every society has access to the multi-trillion-dollar data center that are going to be soon. So compute needs to be as cheap as water. And for that, I know you asked about how we take it from quote-unquote new ideas and all the way to deployment. But let's actually talk about what needs to happen first. Talking about archaic ideas, the compute paradigm today, the major dimension, is archaic. By the way, I'm not representing Grok or any other startup I'm advising. The compute paradigm today is archaic. It's very similar to how the cars were manufactured before Ford came up with the dynamic assembly line, which is you have a manager and a group of experts in a room making a car. You have multiple rooms. Think of multiple cores in a processor, multiple experts in a room. Think of that functional units. And they would run to the warehouse. Think of the main memory for the parts and the instructions themselves from time to time. And the problem there, it is a hub and spoke design. It has choke points. It's great for conditional temporal execution. The paradigm needs to evolve to the kind of compute we need to do, which is more about large data, because AI is today database learning rather than symbolic AI. And it is more data than was used for weather forecasting or even earthquake forecasting. For that, it needs to flow like assembly lines. So that's the compute paradigm shift. That needs to happen. That's where you get utilization from your silicon. By the way, the value there is so massive, it will subsume some of the value we get from the lower dimensions. The other dimension we need to improve, irrespective of what we're on the compute paradigm side, is improve the compute density per rack. Because your compute element and the memory does the real thing. Everything else is overhead. We'll come to the other one that's not overhead in a moment. We need to minimize that overhead. And that's where cooling and power delivery becomes extremely important. Related to that is memory bandwidth, and because the memory wall, the GPUs are hitting the memory wall. Other compute paradigms may not hit that. The third one, dimension, major dimension, you're probably seeing a trend, major dimensions and sub-dimensions to it. Major dimension is communication. It is between racks, between servers, between chips, and between dies within the chip. These three dimensions will give us, if we improve on them, an order of magnitude improve. That is what we need to get compute as cheap as water. So how do you get them to the market? Interestingly, it is about using the existing building blocks, but arranging them differently so you get the right results, rather than optimizing on the existing manifolds, the way things are put together. That doesn't give you the value. Now, why existing building blocks? Because they're reliable. But you need to organize it at the highest level.
Existing building blocks, let's stick with that and let's open it up to everybody. We've been talking a lot all day about kind of incumbent advantages versus startups. Now we're talking, huge, semiconductors, cooling, huge capital requirements. How do the startups innovate and compete? Again, especially given the idea that we're already building on what we already have. Anybody can jump in.
Yeah, I can take that. So, first of all, I think startups, any new business starting from scratch, really relies on discontinuity. You need to look for discontinuity in the environment before you go, hey, raise my hand and I'm going to do a startup. because that discontinuity gives you the ability to utilize the fast moving of a semiconductor, or not the semiconductor, startup, particularly in the semiconductors, and the ability and the willingness of the industry to come in and invest in that idea. Incrementalism is not going to get your investors a lot, and for you as a, especially in this area, for you as an engineer to try to take that risk, you might as well just work at Google and roll in the money, right? So if you want to do something more profound, you use that discontinuity, you use the ability of capital and the speed by which you execute to create that competitive edge. Startups love competing with incumbents when there is discontinuity, because it takes quite a bit of time for these guys to realize the issue, get through the politics and so on, and by that time it's too late.
Especially when things are moving fast like they are right now. It's extra true. Thoughts?
Yeah, I think clearly building a startup, depending on which space you're in, is a different answer, right? So if you're
How many startups? Raise your hand if you're with a startup. All right.
right, so
A lot, yeah.
whether you're using the foundation models to build applications, your domain and data becomes important. If you're trying to build a general purpose LLM, it's a very tough space to get into. But in the context of this panel where we are focused on chips and compute, I think my view on this is that with every new wave, what happens is the first wave of companies are trying to build very general purpose solutions. And Nvidia, when they came out, certainly today they have training, inference, and on and on. And many other chip startups have been trying to go very broadly in training and inference and whatnot. But I think if you're doing a new startup, you have to be very clear on what you're going to do, maybe relative to either specific new area where there aren't existing incumbents, or alternatively segment the market. And so there's a phenomenal opportunity to segment it. Maybe everybody now talks about inference, then they talk about edge inference, they talk about physical AI, and even within inference, what I'm hearing is there's going to be further segmentation, both inside the data center and across different use cases. So you have to pick a segment where you don't have a dominant incumbent, where you can deliver a 5x value, and that's the way to think about it.
More neat. I mean, with Nvidia, I mean, are we relying because of their dominance? Does that suppress specialized silicon? I mean, it's just de facto. With Nvidia with GPUs, doesn't their dominance kind of in some ways suppress the ability to use specialized silicon, which may wind up to be a better technology, but might not get to market?
Yeah, I think this is a great time for startups because the data center market is growing so fast and innovating so quickly, and everything is changing every year or every 2 years. So that type of dynamic environment is where startups can really thrive. I was listening to Amin Wadat's presentation this morning, and Nvidia's dominance, I'm not so sure. After listening to him, I thought that whatever Nvidia has done now, Google has already done 10 years ago. So it's not that they're the only thought leaders in the industry, but also I was really encouraged that Amin said only 10% of his budget is spent on skunkworks projects. That means there are lots of ideas that even Google can't go after that we can.
But let's push that. Let's say Nvidia bundled a cooling solution. Wouldn't that be a real big problem for you?
Not at all, because our ideas are better than anything that they can do
He
themselves.
will be supplying to Nvidia. He will be supplying to Nvidia. So the opportunities, Nvidia's success shows the opportunity, and it is large enough that there is the monetary incentive, but it also shows the failure points with a single provider in the space. That from the business perspective then looks for alternatives. So all of these folks have opportunities to disrupt.
Actually, I have a point of view, which is that, if you look at the history of our industry, whenever there's been a new disruption, it's been done by a vertically integrated stack. Okay, so if you go to the early days of computing, it was IBM that put a complete stack, which included the chip, the system, their OS, DB2 applications, and they sold these mainframes for many, many years, very successfully. But if you look at the decades that followed, that has been disrupted by, x86, ARM, now RISC-V, Linux, general interfaces like PCI Express, Ethernet, and so forth. Same thing happened in the mobile space, right? Apple came out with a vertically integrated stack, and then people like Google and Qualcomm and others kind of broke that stack apart. My view is that we'll see that in the AI space as well, and certainly very hard to predict whether it's going to be 3 years or 10 years, but I think the pace of change in our industry has only increased quite dramatically.
Well, what Rajiv is pointing out is a very important general principle, which is the big jumps happen when you create a new manifold, which requires that vertical. Once you're a new manifold, when you try to optimize it, you can then break it down and standardize it. And right now, the time is ripe for that big jump, the order of magnitude I'm talking about.
Yeah, but when you look at, even in the chip industry with Nvidia, right? When Nvidia came as a startup, there were already people doing graphic chips. Intel was still the king of the jungle, right? And they found their way of creating that discontinuity. If you look back in the last, I would say since 2015 that I've been watching in Nvidia, this did not happen by accident. They had a thought process about what a GPU could do and what the future held, and they spent enormous amount of money as a public company doing this. And they had the courage to do it and stick to it until it's gotten to this point. But I think the dominance of Nvidia in training is going to be hard to beat. So I don't recommend any startup chip guy going out there trying to unseat them. But in the on the inference side, I think the inference side, the world, in my opinion, is kind of wide open as long as you understand the end market you're serving and you're doing bespoke chips for that particular sector. I think that's still open. Obviously, they have an advantage today, but it's not overcoming. So, yeah, understand the need and go after.
Well, Faraj, you talk about the world being open. I want to ask a geopolitical question. We have, obviously, Taiwan makes things complicated. U.S. passes the CHIPS Act. How much are all these geopolitical issues playing into how decisions are made to deploy big capital and where?
Yeah, it's a good point. It's certainly having impact on where you can go for funding and how much of your funding they can hold. But if you're fortunate enough to live here, there's plenty of money. You don't need to go anywhere else to get the money. You got the idea, and you can show that your investors can make money. I think there's plenty here. They'll seek you.
Yeah, so I'll tell you specifically what we have done, right? So in the last 2-3 years, we do the silicon supply chain, which means folks like TSMC and the OSAT. We also manage our system supply chain, which is ODM, CMs, and the like. What we have done is we have shifted our entire supply chain to make sure that any final aspect of the supply chain is not done in China, because there is, who knows, there is some uncertainty with regard to what could happen. So we've tried to do that. The second thing we've done is, in one of my previous companies, I ran into a supply chain issue which impacted us. And that was a pandemic supply chain stuff. But what we've also done is we've tried to build redundancy. So not just, let's say we're doing system manufacturing in Taiwan, we pick another region as well. Thailand, we have a US region as well. So we try to have some redundancy in the supply chain because we're in a world where things are not that predictable or certain in terms of what could evolve. Your tariffs, as you know, swing from one day to the next. And so you have to have a company that's adaptable, that has multiple resilient aspects to the supply chain. It would be great if leading-edge chips like TSMC's could be built in the US, but we all know that that's not happening anytime in the next couple of years or so. So it's good. I mean, really, I think the initiative to get these chips in the US is important. When it happens, obviously, we are all waiting to see.
This is another reason why one should look at value from the other dimensions, specifically the compute paradigm dimension. Again, not representing Grok, but Grok's chips that are competing with Nvidia's 4-5 nanometer are on 14 nanometer. They are 5 generations, quote unquote, behind. You can get more value by innovating at the compute paradigm level than having to tweak and get value at the lower levels. And by the way, Grok chips are manufactured in US.
We have 2 minutes left. I'm going to ask, since we've been kicking around Intel a little bit, I'm going to ask a question about Moore's Law. You know, we're seeing finally, you know, it seemed the law that would last forever, but we are seeing a slowdown at one point. So maybe Faraj, we'll start with you and come all the way to me, and everybody can answer this question in about 30 seconds. When are we going to hit a wall in innovation because of that slowdown, or if in Moore's Law?
Oh my God. I've been in the business for
Tough to go first.
tech business, yeah, for over 40 some odd years, which for the rest of it means I started when I was in kindergarten. And I've always
You
thought—
were Gordon Moore's, like,
yeah,
you know,
yeah, whatever I was
30th
in, I'm like, this is
party.
the end of it. And then, of course, there's innovation, right, ongoing. I think that I just certainly believe that a lot of the power consumption on our devices are there because it takes such a long time, 7 years, to get a really chip into production. We all create insurance, essentially, in our chips. We put a lot of stuff in there that they don't need to be. So bespoke chips, like spoke, I think that's the future. I think people will need to do chips faster, and therefore you can make it more bespoke, lower power, and more directly to the point. I think that's where it's going.
Nash, we're just coming in.
Moore's law will be compensated, or the slowing in Moore's law will be compensated with, say, the packaging dimension. Also with other kind of computing units, optical, for example, playing into that as well. Optical is not a compute paradigm, a compute unit. Moore's law was a brute force way of pushing things for a fixed architecture paradigm, for a fixed packaging. It is forcing us to look at the other dimensions, and there's enough room to innovate.
Yeah, I have a slightly different take because I'm laser focused on thermal. To me, Moore's law has not slowed down because you're still able to pack twice the number of transistors in the same silicon die area as you could every 2 years. You can keep going. But what's changed is you're not getting power reduction. So what the power, you can pack twice the number of transistors, but now they consume twice the amount of power. That was not the case previously. So it's called Dennett scaling. That has gone. Moore's law is still there. But then how do you make sure that you can continue to deliver higher performance, higher compute performance? By innovating in thermal solutions, so that all that extra heat that is generated by the extra power that's being consumed can be dissipated effectively without compromising on rack density, compute density.
Rajiv,
so it's all about thermals.
I see Kent hovering here, the on-time airline. So Rajiv, last word.
Yeah. So, I mean, a combination of both of these answers. I think humans and technologists are innovative people. So we've done chiplet interface standardization to expand beyond the reticle size and build bigger and bigger chips to address some of the challenges that we've seen. Cooling is another aspect to it. And as people know, we've moved from general purpose computing to accelerated computing, and then acceleration for specific applications is the way to go. And software will have to adjust to take advantage of all of this stuff.
A lot of good learnings here. I know we're out of time. Thank you. Infrastructure has never been more important, and we appreciate you guys kicking off the afternoon. Appreciate you.